Hello, y'all. Darrell Lee Berry Jr. back with another Science Hour. And as more people come along, I'll introduce another idea. I've noticed there's been some interest in like UFOs and things like that recently, which I do have a background in. Wrote about a bit, talked about a bit, haven't spoke about it in a while. Uh, well, a lot in a while. I guess did a few interviews last year. I don't remember when, but I know I did. You can go to my website and you can see the dates of all my interviews and everything. I put it there. And but I was thinking about introducing a metaphysical hour where either alternate the hour at this time or add another hour at another time and talk about metaphysical topics. Since there seems to be some interest in that. So we'll see about that. I'll ask you about that as more people come along. So I see one is here, and I plan on talking today about Einstein. I'm gonna move this a bit. I learned in my physics, my quantum two class. Hey, what's going on, Lisa? How you doing? I learned in my quantum two class about a paper that Einstein wrote on quantum. And what do you think about that idea, by the way, Lisa? I'm doing good. Meeting with my, who I'm pretty sure will be my advisor in graduate school. We're meeting next week on Zoom, working on getting my apartment, and I'll have that reveal sometime in June, maybe. June seems like a good month. So I have like a, this is where I'm going to school, and this is what I'll be studying. I'll make a nice video about that. But everything, all the groundwork is getting laid, so that's fun. It is taking some time away from my studies and all. So I'll be glad to. I have two tests next week. I have a quantum 2 exam and a thermal exam. I don't feel ready for either of them. So I have a lot of studying to do over the next few days. So hopefully I can get ready enough. We'll see. But I've been doing good so far. And I think I have a cool topic today in line with what I'll be taking an exam on. Oh yes, I put in, and I can actually feel the exhaustion too, because I can actually use a break. I think the transition to the summer break will be much needed and appreciated before I go into the what 4, 5, 6 year grind to the PhD. So that should be even harder. So I have to be ready for that. What do you think about the idea of a metaphysical hour, by the way, Lisa? I don't know if you were much interested in like the UFOs and stuff, but over the last few weeks, a few people have been really asking about UFOs and saying they had those experiences. Are you interested in stuff like that? Would you like to hear about uh, uh, unidentified flying objects and outer body experiences and things like that? Maybe I can have a separate metaphysical hour show that I would set up. Good. Ah, cool. Well, I'll see about the other people. What I'll probably do is just have it at a different time then, and I maybe have continue to have this one at this time. And for those who are interested, I'll see when they will be interested, and maybe I'll have something on like Wednesday or something. Wednesday sounds like a good day, like metaphysical hour on Wednesday, and keep my science hour on Saturday. But awesome. Not true, but I mean, I can't really say that's the main focus of mine right now. My main focus right now is physics and science and astronomy. I still have an interest in it, but uh, uh, I explored as much of that as I satisfied myself with that exploration a long time ago. Even though I have a wealth of knowledge or background on it, that I'm sure I could dredge it from the memory. But yeah, it's not necessarily anything I'm passionate about talking about. But if people are interested in it, I'll find out when they're interested, and I don't mind talking about it as well. I mean, it is some interesting stuff. But right now, like the majority of my focus is on physics and astronomy and established science. Put it that way. It's not to say that I think UFOs I think they still are there and things like that. But it's not like we have really evidence for it that we could present at large. So I'm more focused on the established science at the moment. So the topic of today, uh, so this paper that you're seeing here on the right side, and actually let me give it a bit more room here. Um, awesome, sounds good, Lisa. We shall keep this for the 8 o'clock science hour. I'll find a different time for that. And I had a very interesting thing we learned this week. I believe I mentioned, let me move this book over a bit as well over here. So you can see a bit more of it. There we go. I think that's good. So I don't know who said it, but one of my professors has said, chances are if somebody mentions something that's been discovered or something like that, and someone asks, well, who invented that? Who discovered that? If you say Einstein, a lot of times you'll be right. Like, it's not to say that. I mean, obviously, you have to discover stuff to be a scientist, right? Like, matter of fact, that reminds me, I need to do a stream about my research. Like, for instance, in my research, I discovered a trend in the distribution. Oh, actually, I gave a talk on that here. I forgot. It's been a few weeks. I found the distribution of the trend in rotation as it decreased sort of linearly from the center of mass to the about 17 parsecs from the center of mass. I can confidently say that nobody discovered that specifically yet because the data was new, and I'm not, and I haven't seen anybody do any indication of that since the data came out in 2023. I started that in 2024. I can safely say that I was the first to discover that about that constellation, and that's still a small discovery, right? In order to become a PhD, you have to make a legitimate discovery. You have to do original research. That's what this dissertation is. So it's not to say that scientists don't generally make discoveries, but it's just that the discoveries that Einstein made, uh, so many of them are so far reaching. They have impact in so many different fields. And he made such discoveries in multiple fields, I'm learning. At least I said if it wasn't in a container, it's not real. Yeah. You know, I watched a few videos of German earlier today, and it's interesting to see they make the best debunkers because they was in it, and when they say these people are idiots, it's a bit harder than if you just from the outside saying it. So yeah, I was every day is it turns out to be a better decision that I don't engage with them people like I used to anymore. But Einstein, I didn't know he made some interesting stuff about quantum. So this paper that I'm seeing here, yes, he is. He's good. Just like when Ranty got out. These they make the best debunkers. So I'm glad I'm just leaving it to them. I'll increase the size of this paper momentarily. Then I'll reduce it a bit again to so I can write about it a bit. And I lost my where's my uh, oh there it is. So basically, what was going on is um, there's a concept in quantum mechanics where um, is a big debate. It's not a big debate anymore because of stuff like what Einstein did. But for instance, if you look at a quantum particle, even if you look at photons, there's something called entanglement. And I know speaking about the metaphysical topic earlier, I know a lot of metaphysical people, they don't understand it at all. And they try to make it sound like atoms are conscious and your consciousness makes it change. You probably heard somebody mention something like that. That's all wrong. What's going on is you can take, let's say, if you have an element and this element emits photons when it's excited, and let's say there's two transitions in quick succession. The two photons that emit are what's called entangled. They're tied to each other. And what happens with one photon will automatically register with the other. Or if you have two particles, two subatomic particles that are entangled. Like for instance, and actually let me draw this before I come back to the article so you can see some background on what I'm talking about here. So this is for 1225 quantum 2 Einstein et al. And they call it the EPB paper. All right, so there's this particle called a pion. I can't remember the exact official name for it, but it's a neutral particle. It's a small particle. And when you break this particle up, what it does is it turns into an electron and a positron, right? It turns into an electron and a positron. And when this happens, and I tested this in my modern physics course that I did last summer, and that I'm a learning assistant for right now, so I'm able to see other people do these experiments and help them with the experiments as well. When these decays happen, angular momentum is conserved. So conversely, let's say if I was to take an electron, and let's say I were to actually let me scratch that. Let's say I take a photon, a high energy photon, like from some element that's irradiating, right? And I knock that uh, gamma ray into an electron, and I'm forgetting some of the details of this. But let's say this electron is hit with so much energy that it breaks into energy. Like let's say that this electron is broken into energy. What's going to happen is momentum will be conserved, so that let's say if this thing breaks into 3 gamma rays, they will be 120 degrees apart from each other, and each one will have 1/3 the energy of an electron, right? And that makes it makes sense, right? So the momentum is conserved. Each one has 1/3 the energy, and it'll always be conserved. So if this electron broke up into two, then it'll be 180 degrees, and each one will have half the energy of an electron. Because again, E equals mc squared. So you can calculate the energy that an electron will they call it I forget the exact word for it, but it evaporates or is destroyed into energy. And you can calculate how much energy it becomes. And when I did this experiment in the modern lab, it's called the gamma experiment. You put a detector here, a photomultiplier, you put a detector here, and you will get so many pings depending on what element you put up in there that's destroying the electrons, right? And if I was to move one of these things a little bit so that one of these is fixed, and if I was to move one of them so now they're 120 degrees apart, I will get so many pings here. I'll get fewer pings because breaking into three is fewer, but the energy will be 1/3 the energy of an electron. And you could do that for however much you want, but it's just the all of these different uh uh when you have a process that's destroying these electrons and converting them into energy, all of these angles are going on at the same time in the same place. All of these things are going on at the same time, like this. So, but depending on where you put your detectors, you will detect one or the other, and you will detect them according to the frequency or probability with which they occur. And you're able to test this and see that this is happening. Well, another thing that happens with this, so now I'm going back to the pion, right? So I'm going back to the pion, which is a particle that the particle physicists are able to destroy, even though there's a more technical term, but suffice it to say destroy. And it breaks up into an electron and a positron. So basically, this is negatively charged, this is positively charged. And because momentum is conserved, it's breaking up into two particles if it's at rest, right? So if the thing is moving, if the pion is already moving and it's going, well, then you'll end up getting something like this when it breaks up into two, right? But if they set it up so that the pion is at rest, and when it breaks up, it'll always go at exactly 180 degrees. So you have one going this way, one going that way. And because they broke up from the same particle, they're entangled. So another thing that happens is there is a property of subatomic particles called spin. Now, I know when we think of spin, we think of something literally spinning around. I mean, I guess there's only so many words in the English language. They could have just made up a word, but they chose to use the word spin. But this counts spin as a property of some subatomic particles that don't go well together if they're the same. So if a particle is spin up, you can't really put it next to a spin up particle. It's going to be a spin down particle, which when you go into quantum mechanics, when you go into chemistry, and you see how elements are built, you'll see that, when elements fill up these rings of the orbitals, right? They fill them up, down, up, down, up, down. So you have a up, down pair, up, down pair. So it actually refers to a physical testable reality, but they call it spin. What they found is when this pion breaks into particles, 100% of the time, 100% of the time, one particle will have an upspin and the other will have a downspin. 100% of the time. It may vary which one has which, right? It may be that the positron has the upspin and the electron has a downspin this next time. It may vary which has which, but one will always be up, one will always be down, because again, it's just this property that we call spin. uh, they don't go well together. They have to alternate up down to be close to each other in any extended period of time. I guess similar to like if you have a magnet and a magnet has a north and a south. If you put two south facing magnets together, you know that they repel each other, they push away, right? But if I was to take these magnets and put them like this, they'll stick together because they have a north magneting to the south and a south magneting to the north. It's similar to that, right? So what they found is that this down thing always happens. But what they've also found is that they can measure just one of these things and automatically know what the other one is. Now, looking at it from the classical perspective, that may seem unremarkable, but another detail that has to be recognized when it comes to quantum mechanics is until we measure the particles, neither of them have up or down. So let's say that again. Each of these particles, they're going to be up or down when we measure them. One is going to be up, one is going to be down 100% of the time. But until we measure them, what we found is both of them have a blend of up and down. And the state that they're in is called the singlet state, where it'll look something like this, where, and maybe I should actually pull this up so I don't write it incorrectly. So it gets a little bit detailed. While I'm pulling up this in detail, let me know if you have any questions, Lisa, or anybody else who's watching on anything I've said thus far. And I'll pull up my professor's notes to make sure that I write this properly. This is something we've been working on for the last few days, so something I definitely was. I was going to talk about quantum too because I have an exam next week, but I figured he had to have been going on over this multiple times because he's going to be on the exam. He's good about that, which is good. I hate when professors like give you an exam and it's something that seems like just came out of the blue somewhere and you don't know where it came from. Um, so I'll make sure to look at this and have a good understanding of it. So, any questions come up? So the act of measuring the spin makes the spin be discretely up or down, like the observer effect. And I'm going to be very careful how I answer because the observer effect reminds me of the stuff I was talking about before, as far as uh, uh, people in the metaphysical realm thinking that consciousness has some kind of influence on a particle. So maybe you can clarify what you mean by the observer effect, but it's not really that. It's just that if I'm thinking about it, like literally the observer looking at it, it's simply that there's a waveform of the particle, but that waveform is not collapsed until it interacts with something. So it's literally that there's something interfering with the particle, and that interference causes the particle to solidify at either a certain location or a certain momentum, and these things carry certain properties with it. So in other words, the entire time you can say people are observing the particle, but measuring the particle involves interacting with the particle, and because these particles are so small, right now I'm writing on this pad, and the pad is basically unchanged. That's why we can write on this pad over and over for years, and it doesn't just fall apart, right? And I'm writing on it with a pen, right? And there's light bouncing off of it. But these subatomic particles, like electrons, are so small. If we send something into it to measure it to see what state it's in, that inevitably alters the electron. So we do get information back about what state is in, but it's altered the electron. So that interaction collapses the wave function and puts it in a very definite state from that interaction. Then it's not the observer effect because it's not the active observation, it's actually interacting with the particle. Nowhere in quantum physics, if you actually talk to quantum physicists, like the people who do it, will they say that's the case? And I know that because I specifically asked this of my quantum physics professor because I have the background in metaphysics, like I was saying before. So my quantum one professor and my waves professor, this is what he does. And matter of fact, my thermodynamics professor, I asked both of them. My thermodynamics professor, sorry, I mean, when I say my thermodynamics instructor, he taught me thermodynamics, but he taught me modern physics. So that class was one third quantum, one third thermal, and one third relativity. But in that class, that professor, he does stuff at CERN. He literally works with subatomic particles. It's what he does. And so as an experimentalist, my waves professor and my quantum one professor, he's a theoretical particle physics. Right. So I talked to one professor who does it experimentally and another who he lives in the world of theory. I asked them both. And what they said was that it's not observing the particle, it's literally that when we measure the particle, we have to interact with the particle. Right. So they're observing it the whole time. They're looking at it, they're seeing it, but just looking at the particle is not going to tell you anything about it because we're not able to we're not able to see it enough fine enough. Our eyes are not that resolved. And when you look at it with an electron microscope or something, inevitably you interact with it quite mechanically, and that disturbs the particle and collapses the wave function. So it's actually an interaction. Yes, the interaction does it. So there's literally you have to bounce some light off it. You have to hit it with another particle. You have to do something to interact with the particle, and that's what's causing the change, not just observing it, right? And I asked both of those professors that, and they confirmed that, right? So it's not what they say. It's just and I used to believe that too because I didn't know any better, right? That is just yeah, you're welcome, right? But you know what happens is a lot of people get this. I mean, it does sound spooky, right? Like the double slit experiment, right? Like the particle goes through both and interferes with itself, and then it's easier to go off on a tangent and say, oh, the observer and things like that. But no, it's just there's literally an interaction with the particle that's doing that. Hey, what's going on, the mathematician? How are you doing? And before I forget, I was going to let me ask you, mathematician. I know you seem very interested in UFOs and stuff. Would you like me to set up a time, a different day, to have something called the Metaphysical Hour show, where we talk about UFOs and out of body experiences and all of the metaphysical stuff, and we can go into that in detail? Let me know if you'd be interested in that, and we can talk about UFOs and all that good stuff and that tip. So I'll look for your reply. Awesome, sounds good. Is Wednesday good for you around this time on Wednesday? Wednesday around this time of this show? Mm, yeah, I could do it on Sundays. All right. And I don't think I have anything scheduled for tomorrow. All right, so tomorrow, yeah. So we'll do science hour on Saturday and metaphysical hour on Sunday at the same time. So I got you. We'll do that. So I'll see you tomorrow for that. And we'll make tomorrow's topic UFOs. Sounds good. So tomorrow, same time. You're welcome. Sounds good. So continuing with quantum. So yes, it's the interaction with the particle. Now, here's the thing. Um, the idea is that and I meant to write the wave function. Let me catch up with that. I distracted myself a bit. So this is the wave function, right? So when you look at particles like this pion, when it breaks into two particles, it's in what's called a singlet state. So this is actually, I know this might be a little bit cryptic, but you can ask me what it means, and I'll recall for you as best I can. But this is basically the uh, writing wave function of these two particles before it's collapsed. Uh, Right, right. So basically, before the wave function is collapsed, before the interaction is done that allows us to see whether this particle is in the up or down state, the two particles together are in this state, the singlet state, where each of them have a bit up or down or up. It's not really clear which one is which, and it's not until they're measured, right, that they become what it is. But the thing is, when this and I keep it'll come to me eventually, the official word, but for lack of a better word, when the destruction happens and we measure this one instantaneously, when we measure this one has the same state. So how does it know? The question is, if we measure this particle, right, before this right here, there's a neutral particle. If the measurement is here, when the particle is here, is pretty much both. Just like how the electron goes through both, the photon goes through both slits in a double slit experiment. Here, each of the particles are both. Here, when they measure it, it becomes one. So how does this one over here know that the one over there became that? How does it know? Like, how does this one up there know that it should be down because the other one has been interfered with and measured as up? And that's the question that came from this paper. Awesome mathematician. I'll see you there tomorrow. So he'll be here before everyone. And that's what this paper was talking about, right? So the question was, all right, there must be some kind of hidden variable. There must be some kind of hidden variable in quantum mechanics where there's something going on. We don't know what it is, but it's something else that's there and that's hidden within the particle, beyond our ability to know, maybe beyond our capability to know. But already, even though we couldn't really tell it, this particle knew it was going to be down and this one knew it was going to be up. And this is what the hidden variable says. Einstein was arguing, if I understand it properly, that no, the hidden variable is not the case. It can completely understand reality. Thanks, mathematician. I appreciate your saying. I'm glad I could I help be a good source of information and entertainment as well. So this is what this paper is talking about. So why don't we look through it a bit? Let me see here. All right. So it says, and this is Einstein, right? He's the lead person on the paper. And it's also Podolsky and Rosen. Of course, I don't know who those people are, but this paper is a very important paper in quantum mechanics. Right? In complete theory, there's an element corresponding to each element in reality. A sufficient condition for the reality of a physical quantity is the possibility of predicting it with certainty without disturbing the system. And that's why, by the way, Lisa, they mentioned without disturbing the system. It becomes they have to go through a lot of um, they have to do some intricate experiments to be able to determine what's really going on. And I could talk about that as well. They actually won the Nobel Prize for it, one of the experiments. One of the people came and talked at my school. In quantum mechanics, in the case of two physical quantities described by non-commuting operators, the knowledge of one precludes the knowledge of the other. Now let's talk about this for a moment. So in quantum mechanics, an operator represents something that can be measured. So and and the operators have a very unique property, the way that the wave function works based upon linear algebra. So the idea is that if I have a wave function, the idea is that it tells us everything about the particle. Everything that can be known about the particle, this wave function will let us know. If we understand the wave function, we understand what the particle is. And these wave functions, in order to understand something about a particle, you utilize an operator. And the way these operators work is, if I have an operator A, and I multiply it by the wave function of a particle, it will give us a value in that same wave function back. So when you have an operator, when coupled with a wave function like this, if it gives you a value and the same wave function back, this operator is called, well, it's just an operator. This function is called an eigenfunction. This value here is called an eigenvalue, and this is still the eigenfunction. Oh, sorry. Thanks for letting me know. I have to work out some what do you call it? Uh process, procedure to stop myself from doing that. To better able to move back and forth. So and actually I have this maximized. You can't see that as well. So there we go. So what I was saying is, and let me review. I'll highlight what I was saying. So we'll call this A the operator. It's just something that can be measured. Maybe it's the position, maybe it's the energy, maybe it's the momentum. There's an operator there. And there's a wave function. Again, this wave function is supposed to tell us everything about the particle if it's a wave function. And when I couple these two things together, if it gives me some value back and the exact same wave function back, then we call this value an eigenvalue. We call this function an eigenfunction of this operator A. And mathematician says, if you didn't know Alexandria, she is my friend. If I'm not here, she will be here. She will tell me where I am. Awesome. Welcome, Alexandria. I've heard from mathematician that this channel is very interesting, especially when it comes to topics like science. Awesome. Thanks for passing the word to mathematician and welcome, Alexandria. Good to see you. Let me know if you have any questions. If anything comes up, I'll do my best to answer. So that's basically, now keep in mind that this is directly linear algebra. Like you can have a vector in linear algebra, like an actual vector, and you can multiply it by a number, and it'll give you the same thing. It'll give you a value back and the same vector back. So ironically, the way subatomic particles behave, they can be modeled quite accurately using linear algebra. So there's a whole lot of linear algebra in quantum mechanics. Now, where the hidden variable comes in is they're saying uh, there's something else in this wave function that's not there, and that's where the commutators come in. Because let's say you have this operator here. The idea is that let's say I had an operator for position and an operator for momentum. The idea is that we can't know these at the same time because they don't commute. So in other words, if these operators commuted, then the notation for commutation is this. If you see this notation in quantum mechanics, it means I'm taking the first operator times the second operator, and I'm subtracting the second operator times the first operator. This is called the commutator operation. Oh, so ugly double M. So when this paper says non-commuting operators, that means that this equals not zero. So if this equals not zero, they don't commute. If I have an operator A and B and they commute, that means AB minus BA equals zero, and they commute. So what this is saying is that non-commuting operators, neither of one precludes the other. So you may hear in quantum mechanics that position and momentum, they have I believe it's called the Heisenberg uncertainty, where the uh, standard deviation of one times the other is going to have to be greater than or equal to h bar over 2. Like the certainty and understanding either one is going to be limited. So this is what he's talking about when he says non-commuting operators, not as if one precludes not as of the other, meaning that we can only know so much about X and only so much about P together because their sum, their multiple, their product is going to always be greater than or equal to that. Let me see if there's any questions that came up. Adriana, don't say a name. Yep, mostly Saturday and Sunday. And that's mostly because I'm in school, Alexandria. Like I'm a full-time student. I'm a senior at UT Austin. I'm graduating in May with a bachelor in physics and a bachelor in astronomy. So through the week, I'm just like busy. But metaphysics, I'll be able to do that to in the Wednesday because I pretty much know that topic. I have a lot of background in it. I could do that either way, but a heavier topic, yeah, I'm usually studying through the week, so I keep this one over the weekend. Awesome. Good to meet you as well, Alexandra. So I'll be here Saturdays for science hour and Sundays for metaphysical hour. But during the summer, because I'll be out for the summer and studying it a lot, I might even do some extra shows throughout the week. So I'm pretty sure I'll do that. So that's what I was talking about with commutating. Then he says, in either the description of reality given by the wave function in quantum mechanics is not complete, or these two quantities cannot have simultaneous reality. And the way my professor describes this is like if I have a particle, let's say I have an electron, and I measure that electron, and I know that it's here, then I can't know much about its momentum. And momentum, by the way, is mv, if I recall, mass times velocity. So this electron is going to be moving, right? They're pretty much always moving. It has a mass. It's going to be moving with a certain velocity. So it has a certain momentum and is moving through space. So it's going to be somewhere. That's position X. But if I know position X with 100% certainty, because these operators do not commute, I'm going to know its momentum very roughly. I'm not going to know its momentum very precisely. Or if I know its momentum very precisely, so I can predict where it's going to be, I can't necessarily know where it's at now. I can just have a high probability of where it's going to be. It's pretty weird. You can't know these two things, X and momentum, simultaneously to a very high degree. So what Einstein is saying here is, okay, that's the reason why they mentioned the hidden variable. Since I can't know these two things very precisely, it either means there's something we don't know about these particles, or one of them can't be real while the other one is real. Like once I know where this particle is, its position is real. I know where that is there. Well, momentum at that time must not be real. Or if I know its momentum and I can't know its position, the position, it can't be a real position at that time. It is in some kind of quasi position, right? Unlike a macroscopic particle like my pen, I know exactly where it's at. I can measure how fast it's going. Those who've been here for a while, you remember how we did the uh uh you know Newtonian equations, 1/2 gt squared plus uh g, what is it, gv plus x, I believe it was. Off the top of my head, I usually have the right gt. No, yeah, just vt. There you go. I believe that's the equation. You remember this equation here, fix for position. So we can know position and momentum at the same time. We can just take the derivative of this and get uh, uh, velocity. Uh, we can multiply by mass and get momentum, and we can know that. We can't do that with quantum particles. Thanks, Catherine. I appreciate the post. So that's what it's talking about. Then he says consideration of the problem of making predictions concerning a system on the basis of measurements made on another system that had previously interacted with it leads to the result that if one is false, then two is also false. One is thus led to conclude that the description of reality as given by the wave function is not complete. So that part is a bit more cryptic to me as well. Not every single thing in this I understand. But what I'm going to do is I'm going to talk a bit about the experiment that resolved this, right? So now you have a little bit of a background of where this is coming from, right? The idea is basically that in quantum mechanics, we can't know these two things at once. So either we don't know everything about the particle, or these things, one or the other, are not real at any given time. How are we going to resolve this thing? So this is what they did. And it might help to have some visuals. Let me bring some visuals up. My professor actually gave us a very good description of the experiment. So I'm going to actually put that image up here that my professor shared with us in our lesson these last 2 days. I have an awesome quantum mechanics professor. Don't worry about that being blocked. I'm maximizing this so I can get a very good screenshot of it. So I have that, and let me add an image so y'all can see what this experiment looks like. Oh, and mathematician says, can you please do one simple question I'm having a doubt on? Uh, uh, I'll send it over, Professor. I'll see. I do remember you, ABCD. Welcome back. Good to see you. Good to see the regulars coming back. I do remember that name. So this is the Bell experiment, by the way. This is the experiment that resolved this thing. And now we know that there is no hidden variable 100%. All right, so now y'all can see the experiment. So this is called the Bell experiment. Now, and I'm going to go ahead and describe what this is. So if you look at the top left, and maybe I should open this in Paint. No, that's good. So if you look at the top left, what you will see is there's a mirror, the thing called C1. I guess it's not necessarily a mirror. It's more like a partial mirror, partial lens, where it I guess mirror even I guess I don't know what's the proper word for it, but it partially lets light through, or it partially lets the photon through and partially refracts it. So basically, if you look at S in the middle, there's an S in the middle, that's the source. And what this source is shooting out photons. It's similar to what we were talking about earlier, how you can shoot out photons and they could be entangled. They have a source that's shooting out two photons, and the photons are entangled, and they have it set up that they conserve momentum, and one goes to the left and one goes to the right, right? So these two photons are coming from the source. They're hitting C1 and C2, and one is getting partially reflected and one is going through. Now, if you look at the boxes, there's boxes towards the left that have a horizontal slash in it. What that thing is, it's actually a standing wave. So they actually made a device that allows a a a photon to either go through or be refracted, be altered, so that it doesn't go through. Right? It's very interesting because we talked earlier about when you measure something, you interfere with it, right? So the problem that we're having is, how are we going to understand what's going on with this? How are we going to understand that, hey, there's something else going on, and it's not just us interfering with the particle, when the only way we can measure the particle is to interfere with the particle. So this is what they decided to do. And let me actually give you a bit more, make sure this is clear. This box here with the slash in it, there's a standing wave in there where there's air in there, and you have a device in there that's making a sound wave. And the sound wave is going in phase and out of phase, such that when the two waves are in phase, they cancel each other out. And it's like there's no wave there, and the photon goes straight through. And when they're in phase, they add to each other, and they put up a wall, and the photon doesn't go through at all. And so this is very important. Inside that box with a slash, at a alternating frequency that's very fast. I mean, photons go very fast, so it's not going to go. It's not going to preclude the photons from going through. But what it does is there's periods of photons going through and photons not. So when the photon goes through, it's not interfered with at that point, and at the same time, there's a detector back here that in such a way, um, it's like the thing polarizes it in such a way to where only a certain photon of a certain polarization gets through in the first place. So in a sense, they already know what they're going to get, but not because they interfere with it. It's because only that thing gets through anyway. It's quite ingenious. So what they were able to do is they were able to do this and confirm that what happens. Oh, and another detail, by the way, if you look at the arms are like 6 meters apart because the original experiment that they did, the arms were so close that the argument was made that um, information could travel at the speed of light. So perhaps there is some kind of communication going on between the photons that's happening at the same time that we can't detect. Where well, these particles are far enough away that even though it's like only 12 meters, they're far enough away that by the time the polarized particle gets through, and we know it's a particle that's only facing this direction because only those particles go through, the particle on the other side didn't have enough time to know what happened to the particle on the left because there's too much distance between them, and thus it was able to eliminate that. And there's a few other things up in here as well that professor went into that I would have to look into more to understand fully myself. But suffice it to say that this is a very advanced device that they utilize to eliminate all the different reasons people were putting forth of why the hidden variable can't, is real. And they totally eliminated the possibility of there being a hidden variable because they showed that these particles, these in this case, these photons, always have the up-down effect, even though one is not determined in even though one is determined without the other having enough time to find out what happened to the first particle. So it's quite interesting. Hopefully that was clear. Let me know. Awesome. So, but that's the stuff that we're learning about. I'm pretty sure this is going to be on the exam. I'm going to have to look at it again. Now, when I say it's going to be on the exam, the professor's really good in that he you know he asks us concept questions about things. And oh, and by the way, did you all see my wave thing? This is what I was writing for the wave thing. By the way, the little box with the dash on it right there. That's the standing wave thing. And either the waves are in sync and they block the light from going through, or the waves are out of sync and it's like no wave is there, and then the photon just goes cleanly through. And there's some other device up in there where they know it's going to have a certain polarity. It's amazing, but they won a Nobel Prize there. It took them a little while to win it, but they won it. Let me know if you have any questions about that. Hopefully that was clear enough to understand what's going on and how Einstein input added to this, and eventually they devised this. This is called the Bell experiment. The Bell group devised this experiment to show uh, uh, um, that these particles do have this coincidence, even though they're far enough away to where there's not enough time for them to interact with each other to like tell the other one what's going on. And now we know that there's no hidden variable there. That uh it's just Einstein was upset about it because he called it spooky activity at a distance. Right? Einstein thought it was some kind of metaphysical thing, and he didn't like that. But this experiment showed that it is going on. So apparently, no matter how far these things are, right, these things could be a light year away. And once you collapse the wave function of the other one automatically collapses to the opposite. The one collapses to spin up, the other one automatically collapses to spin down. They could be a light year away. And even though they don't collapse until they're a light year away, if they're entangled, it's always going to be up or down out of the way. And that it just is we don't really understand why that's happening. It was behind it, but we know it's happening. And the mathematician says the function, let me see if I can write this down here. I believe it is amazing. So the guy who actually did this, not this experiment, but the first one, he came to our school and talked. He was actually very arrogant. Actually, the professor mentioned that in class too. What a big ego this guy had. Let me uh let me take some of these things off, and I'll look at the mathematician's problem here, and then we'll close up. So I'll take that off, and let me center this. So we have the function y equals 1 over 1 plus x minus 2 to the 1/2, y equals 0, x equals 2 to 6, I believe. Revolved around the y-axis. Find the volume using Washer method. Oh, it's going to take a while. But let me give you the theory, by the way. As a matter of fact, this is similar to how I solved that problem. Remember that area problem we did? This is similar to that. Um, and it's been a while since I did Washer. We had to do this. I have to look it up. That's why I do tutoring. That's why in my tutoring, by the way, I plan the tutoring ahead of time because what I do in a tutoring session, I actually review this stuff to make sure I remember it. Hold on. Not x equals 2 and 6. X equals 2.6. 2.6. So so basically we have this, I see. So we have this function. It's revolving around the y-axis. We want the volume of this. So basically what he's saying is we have this. I don't know off the top of my head what this function looks like. But let's say the function looks like this, right? And then we're going to revolve this function around the y-axis. But then you have this volume, and we want to know what this volume is. Yeah, it's been a while since I did Washer. I got an A in the class, but can't remember off the top of my head the details of this specifically. But another general idea has to do with similar to the problem that we did before. We had that problem where we had I remember what it was. We had 4 circles, is what it was. At least I hip you to the fact that it was actually 4 circles. And we needed to get the area in the middle of these things, or if I remember right. So we had an area that looks something like this, uh, something like that. But no, no. What it was a square with some circles is what it was. And we need to get the area. We need to get the area of this center part. That's right. So what I did was I put this thing into a quarter, and I took just the area of this part, and I solved for the line. And all you have to do is basically the first thing I would suggest you do is find the area of one of these things. And once you find the area of one, you could basically multiply it by the 360 degrees around through integration and find out the volume. That's the general basics of it, right? So basically, if you look at it, the volume is like x, y by z, right? So you can call this an area, and you can call this a height, uh, right? So if you get the area of this, and then you can multiply it around, and then it will give you the same thing. I guess maybe we could do. I guess actually it's probably better to say width, and this is length and height, which would probably be the more accurate way to do this. We can say this is length, this is height. It goes out, the length changes. So what you'd have to do is get the equation of this line here, which they give you. They give you a y. You can get this in terms of y and x. You find out what this is. You find out what this is. Get the area, and then you can integrate that area from 0 to 2 pi, which will be 360 degrees around, and this will give you the volume. That's your general idea of it. Yes, it is very hard. But this is the kind of stuff you'll want to get tutoring for the mathematician. So it's not something that I could answer in like 5 minutes. But like I said, if you get a tutoring session, let me know ahead of time what you want to do. Like my tutoring student now, right? Uh, takes too much time at petition. Like I said, I need to review this stuff. I mean, I know how to do it, but the last time I did Washer was in 2023. So I would have to refresh myself, right? I mean, I would have to refresh myself for it to make sure I give you the details, and that's why I plan this stuff. like my tutoring student, what he does is like he sends like, his he's in high school, so his dad sends me an email. Hey, he has to do like last week he did, what was it? It was we was using a pendulum. He's like in AP physics. We were doing like a pendulum. We were doing simple harmonic motion with a spring. So hey, he said me say, hey, this is what he's going to do. These are the products he has to work on. All right, so then I go get my textbook, the textbook that I utilize. I refresh myself, remind myself. I make a lesson plan, and we get together. The first part of the session, I say, hey, this is what we're doing. I go over the theory with them, and then I say, okay, let me know which problems were the hardest problems for you. And then he says, this problem, that problem, that problem. Then I work the problem for him step by step, right? But I have to refresh myself on that stuff again, right? I have to refresh myself on it. So, you know, no, volume is not the same thing as area. So this right here would be area. So area is 2 dimensions and volume is 3. So if I have length, I have width, I have height. Length and width is area. And then if you multiply it by height, you get volume. So if I was to put this in a cube form, right, we can say that this is length, we can say that this is height, and going into the page is width. So just this front part, just this one part here is area. But then when I take this area here and I stack it side by side, so you have to imagine I have a flat space, but then I stack a whole bunch of these back to back. Now I have volume. Now I have thickness. So area times a length or times a height is volume. So that's why I said one way to look at this problem is get the area first. So if you go back to that video I did when I solved that area problem, you could look at that as the first step of one way to solve this. You get the area, and then you integrate that area over the other dimension, and then you get the volume. Right? That's a rough estimate, but again, I have to review it myself to remind myself of the details, and I could give you a very detailed instruction. Awesome, glad it makes sense. So awesome, guys. Hope y'all enjoy it. I'll be back next week post 2 exams. So I have a thermal exam on Wednesday. I have a quantum 2 exam on Friday. So I'm going to be studying my ass off in the next 2 or 3 days, trying to make sure that I do well on it. Yes, it does. Yes, it does actually. But you could check that link there. You can get the details. The link that Catherine put up. So yes, but generally it's 30 an hour. But I can throw discounts. Like my tutoring student now, he's in high school, so I said it could just be 25 an hour. But yes, it does cost money. So, guess you have to tune in to see. All right, y'all. I'll see y'all tomorrow. Those who will be here, if science out, I'll see y'all next week.